So today we're going to be talking about our augmented approach to generative chemistry. And so I thought I'd start by first giving an introduction to generative chemistry, different applications, methods, and challenges, and then tell you about our approaches to generative chemistry embodied in the Nova Bioster and Inspyra modules within our StarDrop software. But having given you that introduction to the current state of the art, I'm going to hand over to Michael, who will tell you about some of our latest research and development in the field and the next generation of this technology, if you'll pardon the pun, basically focused on transformer models and thinking about how to apply them and what they actually add to this sort of space of generative chemistry that we'll be introducing today. And as Katie says, at the end, we'll be very happy to answer any questions you have, so please feel free to add them in the Q&A box as we go. So first, an introduction to generative chemistry. And the first question is, well, why use it? Why are we interested in this at all? Now, of course, as chemists, we have lots of ideas about how to optimize molecules and how to advance our projects. But quite frankly, humans have limited experience and memories. Any one individual, and in fact, any team can only conceive of a limited number of ideas based on their experience. And even scientists have hidden biases. We all have our favorite solutions to problems and a list of things that sort of didn't work that we don't like to use. And while that experience is very valuable, it can also lead us astray because those rules don't apply sort of universally across all the chemistry and all the projects that we might be experiencing in our careers. On the other hand, computers have virtually unlimited storage capacity, perfect recall of any information they've seen, no inbuilt biases, at least no biases that we don't provide them in the first place, and they can generate new compound ideas far faster than any human can enter them into a computer. And what that means is that computers can explore a much broader range of ideas much more quickly and objectively than any one person. And in the context of drug discovery, what this enables us to do is to very rigorously explore many different optimization strategies. It enables us to make faster progress in our projects and, importantly, avoid missed opportunities, avoid missing areas of chemical space or interesting series or compounds that might provide a valuable route forward for our projects. Now, at a very high level, there are different approaches to generative chemistry, and I've sort of bucketed these into two broad groups. One I've labeled cheminformatics, and the other AI, or artificial intelligence. In the cheminformatics bucket, it's really methods that are based on either manual curation of different approaches to optimize compounds, such as sort of chemistry transformation rules taken from the history of medicinal chemistry or previous projects, or others based on sort of statistical analyses of our data sets, things like match pair analysis, or generalizing that to matched series of compounds based on an analysis of existing series and modifications made in the past. By contrast, sort of artificial intelligence methods work by sort of learning what a drug-like molecule looks like. Based on the history of chemistry, big data sets, it can learn representations of those molecules in a way that enables it to make perturbations and modifications that will generate new molecules that are similar or at least drug-like in their nature. And of course, there are many different approaches that have been explored for this. Generative adversarial networks, autoencoders, and most recently, I guess, transformers have found to be very useful in this space. And of course, there are many others as well. But whatever method that we use, there are a number of challenges to applying these generative chemistry approaches. First of all, they're often difficult to set up and run. Maybe lots of different parameters you have to set, lots of sliders or dials or things to set before you sort of hit the big red go button and start your generational run to create these new compound ideas. And then secondly, what often comes out is a vast number of compounds to consider. Hundreds of thousands, potentially even millions of compounds that can be generated really very quickly. And that means that we have take a long time to triage through those lists to find the valuable and interesting ideas. And one of the reasons this is particularly challenging is that these methods can create a lot of irrelevant results or irrelevant, unfeasible or uninteresting compounds. And just as an illustration of that, you'll see a number of images on the past few slides. And this is the result of asking DALL-E 3 to create an image representing generative chemistry, including chemical structures. And let's just say that it didn't exactly hit the nail on the head. So given those different approaches, the objectives and challenges for generative chemistry, I wanted to tell you a little bit about our approach and how we think about this problem and how to apply it in the context of drug discovery. This really falls under the umbrella of what we describe as augmented chemistry. And this is illustrated here. For a long time, AI-assisted humans outperformed both unaided humans and independent AI chess players. This is the first place that this idea of augmented intelligence really came into its own. The concept here is that humans can provide that sort of strategic overview and an understanding of the objectives that sort of AIs will typically lack. But an AI can provide that sort of raw processing power to provide a very rigorous exploration on a tactical level of those different strategic options. Now, while this was first demonstrated in chess, this advantage has more or less gone away in chess. As AI has improved, it really is now, unbeatable. But chess is a relatively simple game with a relatively well-defined and constrained space to search in order to find optimal solutions. Whereas, of course, drug discovery and all of the associated chemistry and biology is far more complex and ever-shifting. And so, realistically, combining that human strategic oversight with AI will always, at least for the foreseeable future, be the optimal approach. And so this idea of augmented chemistry is based on this seamless combination of human expertise and AI algorithms, broadly known as augmented intelligence. So to illustrate this, we call the Inspyra module within our StarDrop software. And this really overcomes some of those big challenges that I spoke about in terms of applying generative chemistry in the context of drug discovery. It enables a human expert to guide and drive these generative chemistry methods to rigorously explore many different optimization strategies. So it removes many of the barriers that I spoke about. Instead of having to do lots of setup, it actually constantly in the background generates, evaluates, and optimizes compounds. It requires minimal setup. In fact, all you need to do is load a data set to get started. So it will generate ideas, it will use predictive models to identify those that are likely to be interesting to you, but it doesn't propose suggestions simply because the computer thinks they're good. It actually learns from you as you work with and interact with those ideas. If you say you like an idea, it says, oh, there's something about that you like. Let's explore that further and understand more about what you like. If you say this idea is garbage, it says, oh, okay, well, let's move away from that and explore other areas of chemical space. So it achieves this seamless combination of expert chemistry knowledge with that sort of rigorous tactical analysis provided by the AI method. And to do this, we've developed what we call an inference engine that infers or tries to understand what you're looking for from your interactions with the suggestions, the ideas, the new compound structures that it's proposing. And what this enables you to do is very rigorously explore many optimization strategies, but very quickly drive and focus those algorithms on those most likely to be relevant and to succeed for your project objectives. Now, underlying that, we have a number of methods for generating new chemistry ideas. This is really focused on generating chemically meaningful ideas based on precedents in the literature and previous chemistry projects. We have three sort of broad methods. We use chemistry transformation rules. So these represent optimization steps explored previously in chemistry projects and curated manually from the literature. So these represent over 29,000 precedented transformations, and they're complete with the references. So if it generates an interesting idea, you can go back and you can see, oh, how was that synthesized? What is the underlying biological data before deciding if that is a method, an approach that you want to take forward in your project. Now, while we have this library of over 29,000 transformations in what we call the BioStir module, that can also be extended based on your experience or your own proprietary chemistry. We also use match series analysis. This goes beyond simple match pair analysis to use longer series of matched compounds. And what that enables it to do is make more relevant substitutions, make more relevant suggestions based on statistically rigorous analysis. To do that, it uses a knowledge base. This is generated from the Chembl database, containing tens of millions of compounds, but it can be generated from proprietary compound data sets as well to represent your in-house chemistry or your own optimization strategies. And as a baseline, we can also simply look at commonly co-occurring substitutions in chemical series. In other words, it's sort of like the Amazon model. Chemists who consider substitutions like yours were also interested in these. And if you haven't considered them yet, then maybe you should be looking at them. And of course, using predictive models, we can suggest which ones are most likely to generate compounds with the properties that you require for a successful outcome for your project. So this applies a broad range of different generative chemistry methods in the context of this Inspyra approach. And I thought rather than just sort of tell you about that in slides, I would drop out of the slides for a couple of minutes and actually just show you what this looks like in practice. And I'm just showing you this in our StarDrop software. So here, what you can see is a small data set loaded into StarDrop. This is a small series of phenyl piperazines, and I've actually done some analysis to look at the structure-activity relationship around a particularly interesting compound here in the middle. And for the purposes of this, all you need to really understand is these red arrows represent essentially activity cliffs, small changes in structure that drive a big change in activity. So let me zoom in here on this one. You can see in the middle here, and what you can see is that the two structures, they differ only in the replacement of a pyrrole group by a phenyl here. You can see a score against a multi-parameter profile, but particularly two things you'll notice is one is the compound on the right is significantly more potent than the one on the left, about 1.5 log units. This is experimental potency. But unfortunately, it also has significantly higher predicted inhibition of the hERG ion channel. And so that poses a significant risk to that compound. And so what we might like to do is to think about strategies where we can retain this phenyl group, which is very good for the potency, but also make some modifications to mitigate that risk of hERG inhibition. And so if I select this compound, it's copied into the designer here on the left where I can make some modifications. And if I'd like to use the information from the predictive model, I can actually use what we call the glowing molecule that lights up the compound to represent the structure-activity relationship recognized by that predictive model. So the red regions here tend to increase the hERG inhibition. The blue regions tend to decrease the hERG inhibition. And it probably won't come as a huge surprise to many of you that this basic nitrogen associated with the lipophilic aromatic group, it's a classic hERG pharmacophore, and that's tending to increase the hERG inhibition. So of course, in the designer here, I can edit away and I can try some things, maybe change this phenyl into a pyridine. You see that makes a slightly blue region. And indeed, you can see that the hERG inhibition, the predicted hERG inhibition has gone down slightly, but it's not a huge change and certainly not enough to be really interesting. I could play around and try lots of ideas here, but this is where I can actually apply Inspyra to help me to explore many different optimization strategies. So what I can do is say, well, actually, I'm looking to optimize hERG inhibition, so I can select that as the property I'm interested in. And then I can simply select a region of this compound, in this case, that basic nitrogen and the phenyl, the benzyl group there. I can select those. When I select it, it goes away and generates lots of ideas, and you'll see it's starting to generate some suggestions for modifications to those compounds. The first few are some simple changes, like the one I just showed you before, like the pyridine substitutions here. But as I scroll through this list of substitutions, you'll see it comes up with another few ideas here. Actually, it's picked up that pyrrole as a possible idea. You'll see this blue sort of circle around it tells me that that substitution is likely to decrease the hERG inhibition relative to that compound I was editing. So that's something we sort of know already from the existing chemistry. But if I scroll a bit further, it's coming up with more ideas. The ones with a red circle tend to increase the hERG inhibition. Clearly, that's not interesting. I don't want to make it worse. But as I scroll through here, you'll see, here we go, a deep blue circle. And this is suggesting actually making a substitution to change that basic nitrogen into an amide. Now, that looks like an interesting idea. So I can click on it. It will make the substitution. It will update all the predictions. And here you can see that, yeah, the score has increased. And you can see a significant, almost a log unit decrease in that predicted hERG inhibition, and still retaining some reasonably good potency. You'll also see, while I've been talking to you, it's gone away and started to generate more ideas. So it's taken that first suggestion, it's put it back in and said, oh, let's see what we can do as that next step in chemistry space. And you can see some combinations of ideas, like adding the pyridine back in here as well as that the changing it into an amide. And again, I could scroll through those ideas. But equally, I like this idea in the back. So I'm just going to click the arrow button and add it to my data set. So there it goes back in the data set. I can sort of park that card representing that compound somewhere convenient. So that's one way we can use Inspyra as this sort of helping to guide the sort of directed redesign of specific regions within a compound that we might be looking to make replacements or substitutions. But we can look at this in another way, which is I can click on this arrow button and it will open up a panel containing 5 ideas generated from all of the compounds in this data set. So it's taking all of these as input and generating lots of ideas. Now, all of these have actually we're looking to optimize a multi-parameter profile here, and it's not doing very well so far. These blue borders suggest that it's actually decreasing this overall multi-parameter score. So I don't want to do that. Here's where I can provide some feedback and say, well, actually, I'm not interested in that. I can reject this idea. I can start to reject some of these. It very quickly starts to learn what I am looking for. So you see these red regions are now appearing where it's suggesting compounds that are predicted to have a significantly higher score than the compounds in this data set. So now we're seeing scores of 0.5, over 0.6 and so on. So these may look like some really interesting ideas. You'll see every now and again it suggests a new substitution. So if we like one of these, again, we can add it to our data set. You'll see it's been added in there as well. We can keep adding these new compounds into our, been added here, into our data set. So again, now it's generating this vast pool of ideas, but it's recognized we're looking to improve this overall multi-parameter score. So it's suggesting more and more ideas likely to achieve that outcome. I can keep adding them as much as I wish. Finally, I've generated some ideas that are added to my data set. I can see that as a table as well. I just wanted to point out that in addition to this, it's also registering these ideas in StarDrop's new idea tracker. So it's actually saying, oh, this idea was created by me. It was created on this date. It's a new idea. I can make a note in here. I can say possible idea to fix hERG problem. So that's now shared with all of my colleagues. So if someone who looks this up, and I might promote this to say, not only is it a new idea, I actually want to put it into consideration to validate that idea for synthesis. And so anyone now looking at this project will have this new compound, will track that note, and see that that's as a prioritized for idea validation. So that's now tracked for future consideration in our project. So again, just a quick sort of example of how we can use this approach to explore many, many different optimization strategies using this broad range of generative chemistry methods. But with that introduction, I'm going to hand over to Michael now, who's going to tell you more about how we can actually take the next generation of generative chemistry approaches and apply transformer models within this broader context. So over to you, Michael.
Okay, so this is our sort of current picture of how our Inspyra generative chemistry module works. We have the inference engine in the center, which is the machine learning algorithm that works out what the user is looking for in a compound or a fragment. The user interacts directly with that. It provides suggestions to them. They like or dislike those suggestions, and that is used to update the pool of user compounds, the compounds in your data set. Those compounds are used as the sort of seed compounds for the next generation of compounds by transformation libraries like Nova, and the compounds generated from that are then sent back into the inference engine to find the best compounds to show to the user, or the compounds that it believes the user is most likely to want to add to their data set. So we have two different algorithms here. We have one that is learning what the user is looking for, and we have one that is generating new compounds. But there's a missing link in this diagram. We're not using the information that we've learned about what the user is looking for to guide the generation of the next set of compounds. So the natural evolution of this idea is to add in this missing link, to take the information that we've learned about what the user is looking for and to directly use that to generate compounds matching those goals. And this is where the generative AI part of this comes in. And this gives us two things. Firstly, it gives us better compounds, ideally compounds matching what the user is looking for, rather than randomly generating compounds and then filtering them down. But it also gives us a really nice way for humans to control this generative process. You can train a generative AI to optimize for any number of parameters, but it's always going to compromise on parameters outside that specification. And that means that it can quite easily generate compounds that perfectly match the goals that it's been given, but which a human expert would immediately disregard because they're flawed in some fundamental way that the generative AI hasn't been trained on. So by having this feedback loop running the whole time with the human expert supervision and the generative power of AI, we kind of get the best of both worlds here. So how do we go about designing a system that can do this? How do we design a machine learning model that can produce compounds optimized for some goal? So as I said before, what we want is a generative model that can take some representation of an input compound, compounds from the user's starting data set, a goal of parameters learnt by the inference engine that say what the user is looking for, say they want HERG to go down, and then it needs to output compounds that are related to the starting compounds, but with optimized parameters, parameters matching the user's goals. And it's also very important to us that we see added value with this process. We want to see methods that complement our existing generative tools, the transformation libraries. We don't just want to be trying to sell this purely on hype. We want to see that this is adding new compounds that we otherwise wouldn't have seen, that the AI is providing a level of diversity to the generated compounds. I'm not going to say creativity because it's not really how AI works, but it provides things that we otherwise wouldn't have seen that are maybe different and more unusual while still being reasonable, synthesizable, desirable compounds. So the approach that we've taken is to use a modified design of the transformer architecture. So transformers are the machine learning model class that powers the large language models. So things like ChatGPT, Google Gemini, that kind of thing. Those are all based off transformers. The way that we've modified it is to add this goal embedding layer or goal embedding module to the design, which takes the vector goal that the inference engine has learned, the parameter objectives, converts that into an embedded goal, matching the internal dimensionality of the transformer's latent space, and then passes that whole thing to the decoder. So we have three parts of the model. There's the encoder stack, which takes an input compound, transforms it to a latent representation in some high dimensional space. We then have the goal embedder that takes our goal from the inference engine, matches it onto that space, puts it onto the same dimensionality, and then this combined sequence is passed through the decoder stack, which outputs output compounds, which are optimized to match that goal. So this gives a really nice way of getting this goal information in there. The alternative is generally to convert that goal to like a string, a series of tokens, and then append that to the smile string, pass that whole thing through, and treat it as a text-based exercise. We've found that by doing this as a vector-based approach, this gives smoother, faster training, and we don't see any difference in the final performance. Also, by doing this as a separate step, it means we can preserve a unique encoding for each input compound, independent of what we're trying to do to it. So if we want to retrain the model for a different set of goals, different chemistry or something, we can keep the encoder stack fixed. That means less training, less risk of things like overfitting, and faster training. It also means that if we want to use this for other purposes, we have an in-house latent representation of compounds that we can use for other models, like predictive models or synthesis models and so on. So I talked briefly on the previous slide about string representations. There are sort of two main representations that you could use to input compounds into a machine learning model like this. It's graph representations, which are a sort of natural representation of small molecule structure. It's a molecular graph. It makes sense to think of it as one. So these are usually represented by what's called an adjacency matrix, which describes which nodes in the graph are related to which other nodes, and a feature vector, so what describing each of the nodes in the graph. What is each atom in the graph? What are its properties? So these are really easy to operate on mathematically because they're matrices and vectors. It's a kind of natural representation of the compound, and you don't have to worry about syntax or anything. There is essentially one standard representation here. The downside is that this is a very complex representation. This is very hard to parse. Like I can look at that big adjacency matrix in the left-hand plot, and I couldn't tell you what that molecule looks like. I couldn't tell you what this is. If you look at a string, on the other hand, that's very simple. That's very easy to read. That's a very concise representation of the data. I can tell you what that looks like. I could draw it on a piece of paper relatively quickly. I can read it. It's easy to store. It's easy to move around as a data format. And the other big advantage that strings have is that they're strings. Transformers were built to work with human language, to work with natural language. And much of the sort of machine learning ecosystem is designed for handling language, so text strings, which means that there's a huge abundance of tools for working with this kind of data. I mean, it's really easy to get this kind of stuff set up. Ultimately, I suspect that while the representation that we choose matters a great deal to structuring the deep learning model in the first place, I suspect it has a relatively low impact on the end result, because the AI is essentially going to derive its own internal latent representation of this compound anyway, regardless of where it started from. So we've gone down the string route because it's much easier to work with and seems to offer just as good performance in the large-scale testing. Now, the most important thing once you have a basic model architecture set up is your training data. This is the thing that makes your model live or die, is getting a good training data set to work from. If your training data set is bad, then your end result will be bad, and there is nothing you can do about that. This is why the big deep learning natural language companies like OpenAI spend hundreds of millions of dollars on training data. So what we started from is the Chembl small molecule database. We started with 1.8 million small molecules, drug-like compounds, etc. We passed them through a cleaning algorithm, get rid of anything with undesirable features in it, atoms that we wouldn't want to be in this kind of data set that we don't want the model to be producing at the far end, get rid of duplicates, that kind of thing. So we're not unintentionally biasing the model to produce the same molecule all the time because there were 10,000 copies of it in the training data. We then run it through a clustering algorithm to identify closely related compounds. So this is similar to doing matched pairs, but a little more flexible. We're looking for compounds that are closely related in fingerprint space, but not too closely related. Once we have those clusters, we can select pairs of compounds from within them. So we find an input compound, an output compound, and then we can look at the parameter difference between them. That gives us our goal vector, and we can convert this to the same kind of goal vector that we use for the inference engine. So this is essentially matching what the user information would be providing. This gives us somewhere between 20 and 100 million compound pairs and a vector difference between them. And this vector difference that we're selecting for here is essentially a parameter space. We're finding loads and loads of different vectors, millions of different vectors within this parameter space. And by training a model on these pairs of compounds, an input compound, an output compound, and a vector, we're teaching it what that parameter space means. When you give it a vector, it knows now what changes it should make to optimize for these specific parameters. So the next step is obviously validating the model performance. And we have three main goals here. Firstly, we want to see that it actually produces novel compounds. And when I say novel compounds, I mean novel compounds that aren't in the training data, but also I want to see compounds that transformation libraries aren't producing for the same starting point. The next is in principle drug rediscovery. Can we go from a lead-like compound to a drug-like compound, at least in principle? And finally, I want to check that the guided compound generation is actually working. Given a vector of parameters, we're trying to optimize for multiple parameters at the same time. Can it produce a compound that matches those goals, which is quite a difficult task? So the first of these, novel compound generation. We're looking for compounds outside the scope of our transformation library and compounds that are outside the training data set. So almost all of the compounds that are generated are outside the training data, which is perfect. And it also covers a different complementary chemical space than our transformation libraries. So this graph here is showing in red the compounds produced by the NOVA transformation library as a function of cosine distance from the starting point in fingerprint space. And in blue, the compounds that are coming out of the generative AI. And you can see that these distributions, one, they're different, and two, the generative AI is covering a wider space. So we're seeing different compounds, complementary compounds that we otherwise wouldn't see. And the overlap between these two things is actually very small. There's only 4% of the compounds generated by the AI are actually found in the transformation library generated compounds. So that's a big tick there. The next test is novel compound generation. So this is, I gave the model a starting compound and a set of random goal vectors. I just told it to generate compounds. I didn't ask for specific properties. I asked for random compounds related to this starting compound. And these are 12 of the resulting compounds that I selected at random from the 1,000 that were generated. I specify at random here because I want to be clear that I didn't cherry pick these compounds. And they actually illustrate some of the problems that you see with big AI models. Because all of these compounds technically meet the goal that the AI was given, but some of them, while they meet that goal, are actually undesirable to an expert. And the combination of the inference engine and an expert user means that we can identify these automatically and filter them out before they're ever seen, without having to fully retrain the AI on whatever makes these compounds undesirable. So the next test is, can the generative AI get from drug-like compounds to lead-like compounds? So this is a similar thing to the approach that we took with the last test. We take a starting lead compound and an unguided compound generation strategy. So we're just randomly generating related compounds nearby in chemical space and picking the closest ones each time for a set of iterations. And we just want to see, can we go from a lead-like compound on the left to something drug-like on the right? And we use the set of lead and drug pairs from Parola et al. 2010. So this is a very simple strategy. We generate the compounds at random, we retain the closest in fingerprint space, run this for some number of generations. This is a very narrow search. When we did this exercise with Nova, we did a broader search, but for a smaller number of generations. And this is just set by aiming to keep compute costs and time costs low. We don't have a fixed set of transformations within the generative AI. It could generate an infinite number of compounds at each generation. So we fix it to 128 and run it for a larger number of generations instead. So this actually, because of that very narrow, very limited strategy, and because we haven't got the guided generation turned on here, this represents a lower limit on the model performance. And we successfully recovered 13 out of the 60 drugs compared to 9 out of 60 for the transformation libraries. And we have a lot of near misses. So these are hits on the left where we've successfully recovered the target compound, and misses on the right where we've not successfully recovered the compound. And the 3 columns are the starting compound, the target compound, and the generated compound, the closest generated compound. And what you can see generally is that where we've missed, it's quite a complex compound, and it's typically that we've got stuck in a minimum in fingerprint space. We've got stuck in a false minimum nearby where we have the same structures, but not in the right places. And to get from A to B, we'd have to take those structures out again. So our simple search strategy isn't up to the job. So generally, we're pretty pleased with this as well. This is another tick for the model. And the final test we're looking at is guided compound generation. So we're giving the model a starting compound, or some number of starting compounds, and goal vectors, some number of goal vectors, and we're trying to optimize n parameters simultaneously. So for this test, we took the same set of lead compounds, assign 100 random goal vectors, which in this case, we are looking at how close we get to those goals. And we're generating compounds given those starting compounds and those goal vectors. So we're trying to simultaneously optimize 5 numerical QSAR parameters. So in many cases, this is probably going to be an almost impossible task. So we're looking to see correlations here. We're not looking to see perfect matches because that's arguably impossible most of the time, but we're looking for it to get it close. And specifically, what we're looking to see is the fraction of generated compounds that are within the model uncertainty of the target parameter. So this is a metric that others have used in the past. The AstraZeneca team, I believe, used this. So these are the 5 parameters. And what you're seeing on the x-axis here is the target parameter value, and on the y-axis, the generated parameter value. And the shaded blue region is the model uncertainty of the parameter estimation model. So this is how accurately we're measuring log S, for example, how accurately we're estimating log S. And what you can see is that most of these generated compounds are within the shaded region most of the time, which is really nice. We're getting very high accuracy for some of them and less accuracy for others. The problem with this as a metric is that it scales with how uncertain you are about your parameter estimation. So if you look at the 2C9 PKI in the top right, the error bar on that is very large, which means that the accuracy is correspondingly large because most of the points just happen to lie within that error. So we constructed a slightly more rigorous estimate here where we're just looking at the correlation between the differences. So that we've asked for an increase or a decrease in a parameter, and we look at the difference between the starting parameter and the final parameter. And we see here that this is correlated across all parameters. We get a very nice correlation for some of them, slightly more challenging for others, but in general, we get a very good correlation out. And what this tells us is that we are successfully optimizing for multiple parameters at the same time with our guided generative AI approach, which is really nice. So we can basically tick off all three of these tests here. The model is covering complementary chemical space that we're not getting with the transformation libraries. It can go from from lead-like compounds to drug-like compounds, and it can simultaneously optimize for multiple parameters and generate compounds matching those goals. The next step here is obviously to do some of these things simultaneously. So we want to put it in the hands of the chemist and have them generating compounds with the guided generation turned on, with it learning their preferences, and see how quickly, how much faster we can get from point A to point B from a lead to a drug, say, using this kind of technology than if we just did an unguided generative approach with either with the AI or with transformation libraries. And I think that brings us to the conclusions, and I am going to hand back to Matt at this point.
Thank you very much, Michael. Thanks for giving us a great overview of this new sort of transformer-based approach that we're working on in our research team. So just to draw a few conclusions. So, our augmented approach to this generative chemistry challenge is really about getting the best of both worlds, about using the power of AI and generative chemistry algorithms in general, but really pairing that and giving that seamless link with the human expertise to drive that those algorithms to the most relevant and interesting compounds very efficiently. And it does this by inferring the direction you want to go. It's working out what are the property combinations that you're looking for, and the areas of chemical space that you prefer, to very quickly focus in on optimal compounds for your project objectives. And then Michael has described the latest of the sort of generative AI research that we're doing, this sort of vector-based goal combined with a transformer-based model gives very efficient sort of multi-parameter optimization to even more quickly generate high-quality compounds for you as the expert to consider. So we have given you a bit of a sneak peek here at some of our latest research. And so this new transformer-based approach is currently being built into a future version of Inspyra. And stay tuned if you want to see the final outcome. So next, we'll move on to the Q&A section of the of today's webinar. And while you have some few moments to type in any questions that you have, I will just mention in StarDrop and the Inspyra module, this approach to generative chemistry that I quickly demonstrated today really helps you to generate new compound ideas, to explore vast regions of chemical space around your leads or series, and also on that sort of individual compound basis, consider optimization strategies for substitutions and modifications to achieve your objectives. If you'd like to try it yourself and are not already using Inspyra, please do feel free to get in touch to info@optibrium.com. We'll be happy to tell you more about the method and set you up with a chance to evaluate it yourself. So I can see the questions are coming in. Let me just tackle the first of those before I hand over to Katie. There is a question about whether this webinar will be available as a recording. And just to reiterate what Katie said at the beginning, yes, we have recorded this and we're going to publish this on our website in the webinar section, and you'll all receive a link so that you can view it again if you wish, or indeed share it with any colleagues who you think might be interesting. And with that, I'm going to hand over to Katie, who will be moderating the Q&A section.
Thank you, Matt. Thank you, Michael. We have had a few questions come in, but as Matt mentioned, if you do have a question that you would like to ask one of our panelists, please do enter it into the Q&A. So the first question is, can you guarantee that the compounds that are generated are synthesizable?
That's a great question and a very common one. Well, the approaches that we take are designed to generate chemically meaningful or tractable steps in chemistry space. But we can't, using these algorithms themselves, guarantee that they will be synthesizable, i.e. that you'll have the right building blocks and reaction to hand. However, what we can do is link this up to other methods for analyzing the synthetic tractability or looking at sort of retrosynthetic analysis to propose synthetic routes to these compounds. So we do that, for example, in partnership with organizations like Postera and their Manifold platform, or Deep Matter and IC Synth. If you're interested, we actually recorded a webinar, I think it was last year, with our colleagues at Postera to show that link between StarDrop and their Manifold platform to do that analysis and ensure that the compounds are at least very likely to be synthesizable with available building blocks.
Thanks, Matt. The next question that's come in is, what is the difference between this method and ChemFormer, which is AstraZeneca's generative chemistry approach?
I think that's one for you, Michael.
Yeah, so they are closely related approaches in that they both use generative transformers to produce optimized compounds. There's sort of two main differences. One is in the construction of the training data, and one is in the construction of the model itself. So the ChemFormer paper, I believe they used matched pairs for their training. So they specifically look to generate matched pairs of compounds. Whereas we're looking for a more flexible approach. We're trying to generate compounds that are closely related, but not necessarily matched pairs. And in the construction of the model itself, they're using the approach of tokenizing their goals and then adding that onto the input string that they give the model, whereas we have the goal embedding submodel that converts the goal into the latent space of the model.
Thank you, Michael. There's another question that's come in, which is, can I see all of the compounds generated by Inspyra?
Oh, that's a great question as well. So obviously with these generative chemistry methods, you can create very, very large sets of compounds indeed. And one of the motivating factors behind Inspyra is to make it very easy to explore that large and ever expanding space as you're feeding new ideas in. Of course, it's continuing to evolve and move in that chemical space. So the numbers of compounds can be potentially very, very large indeed. So for Inspyra itself, we don't output that full set of compounds. It grows so quickly that it really, what we're providing here is a very efficient way to move and explore through that space. But of course, sometimes you just want to really set up a particular run and generate a large set of compounds to triage through, in other ways to look at sort of in StarDrop or another piece of software. And so we can actually do that through our Nova module. This uses the same generative chemistry approaches, but allows you to sort of set up your specific requirements a priori and then generate that set of compounds, which you can then triage using multi-parameter optimization or looking at sort of chemical space visualizations or other visualizations to focus in on those most likely to be of interest. So we provide both approaches, but through slightly different mechanisms. One uses our Nova module, the other uses this Inspyra approach.
Thanks, Matt. There's another question which I think is around a point of clarification, is just looking to understand whether we're using reinforcement learning to generate molecules optimized for specific properties.
Sounds like one for me. No, we aren't. We're sort of skipping the reinforcement learning step because we have the inference engine available so that we can learn what properties we're looking for without needing to train a full deep learning model to work it out. So we have the generative AI that is pre-trained on a certain chemical space, and we have the inference engine that learns what the user is looking for, but without needing the full architecture of a reinforcement learning model. Typically, reinforcement learning takes a lot of feedback before it is robust, before it has a good picture. So the algorithm that we're using here learns a lot faster what the user is looking for, which means that we can provide optimized compounds for them faster and without needing them to sit there for hours and hours and hours and provide feedback.
Thanks, Michael. There's another question that's come in. So the question says, for the graph evaluating Gen AI cosine distance versus NOVA, there seems to be a significant bimodality in the distribution. Is this potentially due to the ChemBL training data and non-uniformity in the vector distance between pairs in training?
That's a good spot. I actually have a whole slide on this that I cut from this slide deck before the talk. It's really interesting. I quite like this one. So there is a bimodality in the cosine distance between the pairs, but the model, because it works on string data, isn't actually learning that distribution. Like, my naive assumption was that it would be trying to reproduce that distribution. But in practice, what it's learning is the number of differences in the strings. That's the distribution that it's internally trying to reproduce. So if you plot the same graph, but with the Levenshtein distance instead of the cosine distance, so the difference in the number of characters in the string, you get like a unimodal distribution. So this is something I plan to spend more time on in the future, looking at exactly what effect we can have over this distribution. And we probably want slightly more control over the exact compound generation here. So one of the things that we're considering is adding an extra parameter into the generation process to control how far away from your starting point you want to go, the amplitude of the transformation that goes in there. Good question, good spot. Interesting and still somewhat open question as to why this happens.
Thank you, Michael. There's another question that's come in that asks, are there any legal concerns around using AI in the compounds generation process that we should be mindful of?
That's another superb question. Yes, absolutely. And there's a very broad question around sort of the sort of IP and generative AI. So I don't think there's settled case law around this yet, but the sort of strong legal opinion that I have heard expressed is that the inventive step is actually the selection of the compound by the expert chemist. So these generative AI methods, as we've just discussed, can create very large numbers of compounds, but it is that step of looking at the compound and going, yes, I'm going to make that one, that is the inventive step. And of course, that is sort of exactly the philosophy behind Inspyra, which is it is generating and exploring lots of chemistry, but it's guided by the expert. And so really that reinforces the IP in the actual compound structures that are eventually selected for synthesis and testing. So I think this actually provides that sort of reinforcement of the IP position.
Thank you, Matt. And I think we have time for one last question, which is, how does the model recognize less common chemical motifs, such as phosphonic acids or esters? Is it able to provide ideas based on existing data that includes these motifs and expand them?
That's a really good question. So I'll have a stab at that, but Michael, you might want to chip in here as well. So yeah, clearly like any machine learning model, any generative model, I should say, it's going to generate ideas that represent the distribution of the training data ultimately. I think that's fair to say. And so if you have very rare chemical motifs, it is less likely to generate them, to produce them, unless they are particularly strongly associated with the goal vector you're trying to achieve. So, extrapolation is very challenging for any machine learning model. And so I think unless you change the frequency of occurrence within the training set, I imagine that it will only rarely produce these sort of less commonly explored motifs. But I'm probably less the expert here. So Michael, does that sound reasonable?
Absolutely, yeah. The only thing I would probably add is that while it's it's unlikely to add uncommon motifs to an existing molecule. If you have those motifs in your molecule already, then it will preserve them most of the time. It's unlikely to just remove them altogether all the time. Yeah, and like Matt said, it's something that it feeds through from the training data. So the only way to produce a sort of higher representation of it in the generation process overall is to adjust the training data somewhat.
Fantastic.
Thank you
Thanks.
both. Thank you both. Unfortunately, we've reached the end of our time here today, so all that's left for me to do is to thank our speakers and to thank you all for joining us today. We hope you enjoyed today's webinar, and we'll see you next time. Thank you.